Welcome to the course entitled Basics of Fluorescence Spectroscopy. Myself, Dr. Pratik Sen, is the instructor of this course. So, I am an associate professor at the Department of Chemistry here in IIT Kanpur. So, in this particular course, right, we will going to discuss about the basics of fluorescence and its application, starting from the environmental effect, Foster resonance energy transfer, fluorescence quenching, electron transfer, single molecule fluorescence, etc. So, this will be a 20 hours course for the entire 8 weeks. So, per week we will get 5 lectures, 5 into 30 minutes, that means 2.5 hours, and you will be given assignments in every week. And by solving these assignments, you will get a fair idea that how the course is going on, and you will get to know that the other topics on this fluorescence spectroscopy. So, before starting this, let me tell you that few reference books about this fluorescence spectroscopy. The first of all, this book I would like to follow. So, this is the Principle of Fluorescence Spectroscopy by J.R. Lakovich. So, and the second one is being to the Molecular Fluorescence Principle and Application by Velour. The third one is Fundamentals of Photochemistry by K.K. Rohatgi Mukherjee, and the fourth one, which sometime I will also follow in this course, is Modern Molecular Photochemistry by N.J. Turo. Right. So, with this, as I said, so these are the contents. So, we will start with the introduction of the fluorescence, then I will show you the instrumentation of fluorescence spectroscopy, where I will show you how to measure the fluorescence spectra, and to tell that I will also introduce the absorption spectroscopy to some extent. Then I will go to the requirement or necessary of the lifetime measurements, and then I will show you the time domain lifetime measurement, and then I will show you the solvent and environmental effect on this fluorescence. Then I will show you the fluorescence quenching, fluorescence anisotropy, energy transfer, Foster resonance energy transfer, and at last I will show you the latest advancement of this fluorescence, which is single molecular fluorescence. Okay, so to start with, let me ask you that question, that what is fluorescence? Obviously, fluorescence is a kind of light emission from the molecule. To understand this fluorescence, better we understand that what is luminescence. So, luminescence is a phenomena of light emission from a material which are not solely conditioned by the raise in temperature. It is just opposed to the incandescence. In incandescence, that is what you have seen in the normal filament bulb, right, in our houses. So, that light is coming from the incandescent bulb is because of the heating, but in fluorescence this is not because of the heating, right. And this luminescence is termed as the cold light. So, the term luminescence comes from the word lumen, which is the Latin word, and that means light, and was first introduced by a German physicist Weidmann. So, in 1888, and if you want to see the modern definition of luminescence, one can say that this is a spontaneous emission of radiation from an electronically excited species or from a vibrationally excited species which are not in thermal equilibrium with its surrounding. So, as time goes, we will understand the actual meaning of this kind of ultra modern definition of this luminescence, but before telling other thing, let me show you some different types of luminescence. The luminescence, the phenomena, right, is categorized in different types based on the mode of excitation. For example, let us take this chemiluminescence. In the chemiluminescence, the mode of excitation is chemical reaction. So, as you have seen in the glow sticks, right, where the sticks will be broken and it will start glowing. So, that is basically a chemical reaction which evolves the light. So, the glow sticks is now glowing, so you can see in the dark. And like different kind of chemical reactions like oxidation may be caused for this light emission from this device, and these are called the chemiluminescence. Similarly, the radioluminescence. So, radioluminescence is kind of luminescence where ionizing radiation like X-ray, alpha, beta, gamma rays are the mode of excitation. So, which can be seen in the ancient clocks, like the digits and the needles of these clocks are glowing in the dark. So, and the third category of luminescence is the bioluminescence, where in vivo biochemical reaction is responsible for the mode of excitation and which is now emitting light. So, here you can see for the firefly will get this luminescence out of it. Similarly, we have sonoluminescence where the mode of excitation is ultrasound, we have electroluminescence where the mode of excitation is the electric field, and last but not least we also have this photoluminescence, right. We have this photoluminescence where the mode of excitation is absorption of light. So, where the mode of excitation is absorption of light, that means photoluminescence is nothing but the fluorescence. So, here the fluorescence is a special type of luminescence which is known as photoluminescence. So, in one word I can say that fluorescence is nothing but the photoluminescence. That means that when I have a particular molecule in solution or in your media, so like this is not glowing, that no light is coming out of this material, no light is coming out of this material. The light will come out of this material, right, only when it is irradiated with some other kind of light. For example, if I now irradiate this with this kind of green light like this green light I am irradiating, then some new light will come out of this system. Let us say new light which is coming out of the system is type of orange. So, this new light is coming out and this light will come out in all the directions, right. This light will come out in all the directions. So, this new kind of light, that is this orange light, is only present when this system, right, here is your system, this particular system is irradiated with this green light, otherwise not. So, the light emission is because of the absorption of light, or mode of excitation is the absorption light. So, this is called the photoluminescence or fluorescence. Okay. Now, let us ask another question, that what is spectroscopy, because we are going to discuss the fluorescence spectroscopy itself. So, spectroscopy is nothing but the study of light matter interaction, right. So, I have light, I have matter, they are interacting with each other, that is what is going on over here. This is your matter, right, as I showed here, this is your matter and this is your light. The light is interacting with this matter. What is the result? Result is the emission of new kind of light, emission of new kind of light. So, the light matter interaction is basically known as the spectroscopy. So, what is light? Light is wave, we all know. Light is also particle, and this is called the wave particle duality of light, which is connected by the de Broglie, right. So, lambda equal to h by p. So, light has to be treated as wave as well as particle, right. It has a dual character. So, when we talk about the wave nature of light, then we can talk about that light is nothing but electromagnetic radiation where the electric field is oscillating at perpendicular to the magnetic field and both are oscillating perpendicular to the direction of propagation of light, as is shown over here. So, here is say this is electric field is oscillating in this direction and this is the direction of propagation of light, direction of propagation of light. So, this is electric field and here in the perpendicular direction this is my magnetic field. Right, this is my electric field. Light, as you know, light can also be treated as a particle, and this particle is called this photon, and which is this is what I am showing is the famous photoelectric effect, right. So, this phenomena of photoelectric effect was described correctly by Einstein while treating the light as particle, the photon having photon energy h nu. So, light is wave, light is also particle. So, now when light will interact with the matter, I sometime have to take this wave character of the light, sometime I also have to consider the particle nature of the light. Now, question is that the light will come and interact with the matter, then this light will make some change in the matter. If there is no change, then there is no interaction. If there is interaction, that means there is some change. So, there are several type of change. The change could be the change in the electronic state of the molecule, electronic state of the matter, change in the vibrational state of the matter, rotational state of the matter, and so on and so forth. In fluorescence spectroscopy, we consider the change in the electronic state of the matter, right. So, we say that after interaction, the material or molecules, right, consist in this material, they are promoted to the excited state, and several phenomena can take place in the excited state of the molecule, which eventually we will going to discuss in this course, right. So, let us take that you have light which is actually exciting the molecule and putting this molecule in the excited state. In the excited state, right, I can have the fluorescence. This is one property. This excited state can undergo intersystem crossing to get to yield the phosphorescence. This is another property of the excited state. It can undergo some small changes in the molecular framework, and it will give you the conformational change in the molecule, right. It can undergo electron transfer, proton transfer, energy transfer, excimer, many process, and some of them we will going to discuss in this course. So, this is the result of this light matter interaction, right. The result is the molecule will go to the excited state, and in the excited state several process can occur, right. Now, one of them is fluorescence, which is the topic of our interest right now, right, and this particular fluorescence, right, the property of this fluorescence can be used to understand the environment itself. Suppose you have a molecule in your system, in a particular solvent, in water or inside the protein or inside your lipid membrane, and you keep on trying to look at the fluorescence property of the molecule. So, if the environment will change, let us say for example, the lipid bilayer is broken somehow. So, depending on the choice of your molecule, the fluorescence molecule, the fluorescence property may change. Say for example, this famous molecule like CCVJ. So, if you use that molecule, the fluorescence intensity strongly depend on the viscosity of the medium, or the restriction imposed on this molecule by its environment. Right. So, if the viscosity change, the restriction change, right, if the lipid bilayer is broken, then the fluorescence intensity decreased. If it is not, then fluorescence intensity increased, and so on and so forth. So, by looking at the property of the fluorescence, I can have the idea of the restriction imposed by its environment. For example, if you take a famous coumarin dyes, so what we will see that by changing the polarity of the medium, the emission maxima, the fluorescence spectra, right, the color of light, color of emitted light, right, will change. And so, from the knowledge of the color of the fluorescence light, I can predict that the media has a low polarity or high polarity. In other words, whether it is like a water or it is like ethanol, it is or like a propanol, and so on and so forth, right. So, basically I can have a different type of property can be observed, can be measured, can be understood by this molecular fluorescence, like as I mentioned the polarity, as I mentioned the viscosity. I can also measure this pH, hydrogen bond, ions, electrical potential, quencher, temperature, many property, and in this course we will going to discuss on some of this, right. And to continue, let me briefly discuss about the history of this fluorescence, right. this observation of this fluorescence is not new, right. It has been reported long time back. So, in 1565 it was first reported. At that time no one knew that this is fluorescence and what is the mechanism of this. I mean, nothing was known at that time. So, it was first discovered by a Spanish physician and botanist when he was trying to distill some wood sample, right. At that time people are distilling wood sample, this sample, that sample, and when the distillate of that particular wood sample, right, when he put inside inside a glass vessel, like here as I am showing over here, put inside a glass vessel, what he can observe under light is the following. You see here, just change the color. Here you see this part, a bluish tinge, right, is coming out, right. At that time he was very much curious to know what is the origin of this bluish tinge, and at that time obviously the understanding was not that much and it was not been identified as a fluorescence, but he mentioned that when this distillate of this wood has been taken in that normal room light, a bluish tinge is coming out of it, and he first time said that this is a new kind of phenomena, and he said that this is a opalescence or something like that. So, later people know that this molecule is responsible for such kind of bluish tinge. However, the situation was like that till 1833 when David Brewster, right, what he did, he took the ethanolic solution of leaf, yeah, and he passed the white light. After passing the white light from the 90-degree angle, what he can observe is a red light is coming, right, from that light path, right. Now we know that leaf contains the chlorophyll, and this chlorophyll are also emitting in the nature. So, that gives the fluorescence light, and that is the red light what he was observing. So, he was also reported like that way. But the first kind of established experiment was done by Sir Herschel in 1845. So, what he did, he used the quinine sulphate and he observed the quinine sulphate fluorescence, right, from a glass vessel, which I am going to show in the next video. And after that G. Tokes in 1852 actually did the similar experiment, but much more scientific way, and in 1853 G. Tokes coined the term fluorescence for the first time. So, let me show you this Sir Herschel's experiment over here. So, in Sir Herschel's experiment, what he was doing, he was using this church window as a source of light, because the sunlight, all the wavelengths are there, but when the sunlight is passing through the church window, only blue light is passing, because the color of this church window is blue. So, only light of less than 410 or 20 nanometer is passing through this church window, blue color church window. So, that blue light is actually come and hit this bottle containing water, and in this case, as this water is just a scatterer. So, when the scattered light is coming through this yellow glass, which actually not transmit the blue color of light, then Sir Herschel could not observe any light out of it. So, he was just seeing a black thing. However, when he replaced that water in this vessel with quinine sulphate, what he observed, that he can see some color coming out through this yellow glass. It means that new kind of light has been emitted from this quinine sulphate solution, right. Otherwise, if it is just a normal light, you should not be able to see that any color coming out through this yellow glass. So, this was the very first experiment for the fluorescence from a well defined molecule. Here the molecule is the quinine sulphate. So, what kind of light matter interaction we can see? If I have a matter right like this here, so the light can fall and be reflected. So, I have reflection, I have refraction, I have elastic scattering, which is like a Rayleigh scattering. I also have this inelastic scattering, which is Raman scattering. The color of the scattered light is being changed, right. So, this is inelastic scattering or Raman scattering. I will have a transmission or absorption, and later on this we could also have this emission. So, for us the important thing is the absorption of light, right, which triggers the emission, right, or the generation of new light out of the sample. So as said that when light falls on a substance, a part of the light could be absorbed and the rest of the part will be either reflected or transmitted. In most of the cases transmitted, right. And how much light is being absorbed is given by Lambert-Beer law. So what is Lambert-Beer law? Lambert law is the absorbance of a material sample is directly proportional to its thickness. If we increase the thickness, the absorption will be more and more. And Beer law says the amount of radiation absorbed by the medium is proportional to the number of absorbing molecules in the medium, that is the concentration of the molecule in the medium. So what I have optical density is written as epsilon into C into L, right, epsilon into C into L. This optical density is sometimes also called this absorbance A. So here this epsilon is the molar extinction coefficient or molar absorptivity, C is my concentration and L is the length of the medium. So you can write this as a log I0 by I is equal to epsilon CL, and one can show easily that this epsilon is a function of lambda, that is wavelength of the light. Not all wavelength will be absorbed with equal efficiency by the molecule, and this epsilon obviously as is a function of lambda. This I0, right, which is incident light intensity is also, and this I which is intensity of the transmitted light, they also a function of lambda. Now if I plot this OD versus lambda, OD is obviously proportional to the epsilon, which is a function of lambda. So you will get this absorption spectra. This is known as absorption spectrum of the molecule. So here we said that this is the absorption maxima of this particular molecule under investigation. Okay. So ultimately what we got is A is equal to epsilon C L, right. So this is in one word Lambert-Beer law, right. This is Lambert-Beer law. Now if we want to see this Lambert-Beer law in a close view, let us see how we can see that. So this is my cuvette, this is my sample cell as you can see, and I poured some sample with a particular concentration. This path length is L, and I have a lamp of a particular wavelength. So this is some way I can check, I can select the wavelength. This is for the particular wavelength lambda, and I have this initial intensity I0. So let us consider that this particular sample is consist of a infinite number of thin slabs, right, consisting of this length L, and the thickness of these slabs is dl, right. This is the thickness of each slab, and this is infinitely small, and I have infinite number of such slab making it L, so that I can do the integration later on. Okay. So now this light is passed through, and after passing through, right, the intensity absorbed at this position will obviously not be same as the intensity absorbed at this position, right, because light intensity is more at this position and will be less at this position. So as you can see in this cartoon, in this small video, that light intensity means the electric field is very strong at the entrance, but when it is exiting the sample, the electric field is less, right. So it can be detected by this lambda, right. So what I can have, minus d I by I is proportional to C into dl, right. So I can simply do the integration I0 to I, that is 0 to L, and what I will get is ln I0 by I equal to kappa, some constant obviously over here, is obviously depends on the lambda into C into L. So we'll just change from natural logarithm to 10 base log, and what we will get is kappa is a function of lambda by 2.303, which is epsilon, right. This quantity is termed as epsilon over here, epsilon CL. So here A is equal to epsilon CL, a simple derivation. So if I know the concentration, the path length and absorbance, which is a measurable quantity, I will be able to calculate what is this molar extinction coefficient, and this is depends on the lambda, and obviously then this A is also a function of lambda. That what I have shown you earlier, that a plot of absorbance versus wavelength is known as the absorption spectrum of that particular molecule. Okay. So, what is absorption cross section? Let us take again that same type of sample, right, which what I have over here. This is my sample, and I have I 0, and after passing through the sample this become I, right, and this is divided into small thin slab of sample. The path length, as I said, is L, and let us say this is dx this time, right. So, dx, this is thin slab, right, thin slab of sample solution, and let us also assume that it contains n light absorbing molecules per cc, per centimeter cube. So, the light I can write here the light intensity absorbed by the sample is proportional to intensity of the incident light is also proportional to the number of light absorbing molecules and that proportionality constant used for the Lambert-Beer's law here automatically will come as the cross section or absorption cross section of the molecule. So, here is the absorption cross section which is generally denoted as sigma of the molecule, right. So, I can write simply minus di dx is equal to I sigma n, that is it. So, then I can integrate, I can put the boundary condition. What is the boundary condition? It is easy. At x equal to 0, right, dx I am integrating, I has to be equal to I 0, this is the incident light intensity, right. So, I is equal to I 0. So, with this boundary condition after integration immediately what I will get is ln I 0 by I equal to sigma n L, which is the path length, right, integrate from 0 to L. So, this is going to give me capital L, which is the path length defined like this way. Okay, so, L is the thickness of the sample, as you should write some here. L is equal to thickness of the sample. Okay, so, what we got is this. Now, what we already have seen is another equation A equal to epsilon C L. If you remember the Lambert-Beer's law, we already saw A, which is nothing but log I 0 by I is equal to epsilon C L. So this epsilon C L and this sigma N L, they must be related to each other, right. So, now let us see. I can equate these two equations now. I can simply write here sigma equal to 2.303 epsilon L, right, C divided by N L. From these two equations, from here together, I can write this equation, isn't it? Okay. So, just this L will cancel out. So, what we will get is 2.303 C by N epsilon, that is it. So, here C is my concentration defined as moles per liter, and here N is the number of molecules per cc. So, in the next class we will see that how we are going to equate these two to get information about this quantity sigma, which is absorption cross section. Thank you.